Today, we're going to go over the basics of reaction mechanisms. First of all, a quick little recap on the rate of reaction. So the rate of reaction is defined as a change in concentration of reactants or products over a change in the period of time. It has the units moles per dm cubed per second, and there are multiple factors that affect the rate of reaction, including the temperature, the concentration, the pressure, surface area, and also presence of a catalyst. Now moving on to reaction mechanisms. So what are reaction mechanisms? Reaction mechanisms basically describe the reactions and their rate. The first thing that we need to talk about when we talk about reaction mechanisms is the rate determining step. Abbreviation is RDS, which you will see throughout this video. So what is the rate determining step? The rate determining step is defined as the slowest elementary reaction in a multi-step reaction that determines the overall rate. And the rate determining step will have the highest activation energy, hence why it's the slowest. For instance, here is a graph. And as you can see, the activation energy for step 1 is much greater than that of step 2. Therefore, step 1 would be the rate determining step of this reaction. Now let's talk about reaction order. Reaction order is basically the degree to which the concentration of a substance affects the rate. The reaction order can be expressed as a to the power of x, and x being the order. It can be any positive integers, which indicates that it has effect on the rate, or it can be 0, which means that it has no effect on the rate, as anything to the power of 0 is equal to 1. Now let's go over rate equations. So let's start off with the general formula. The general formula for rate equations is R is equal to K bracket A to the power of X times bracket B to the power of Y times bracket C to the power of Z, etc., etc. So what do all these letters stand for? First we have the R, which is also the rate of reaction. This will usually be given in the question. And we have K, which is the rate constant. And K is dependent on the temperature. And as you can see in the graph below, as the temperature increases, K will also increase because the ROR increases. Now, bracket A means the concentration of substance A. And X is the order of A. Now, bracket B is the concentration of substance B. And Y is the order of substance B. So you saw all of those substances that were in the rate equations. But what actually can be included in the rate equations? Well, first of all, substances that are not even in the stoichiometric equations can be in the rate equation. This is for catalysts, as catalysts will also affect the rate, as mentioned previously. However, substances that are in the stoichiometric equations sometimes aren't in the rate equation, as the concentration of that substance will not affect the overall rate. So now that you know the basic concepts, let's practice with a little question. Here, we're given a table with the concentrations of substance A and B and the rate corresponding to the concentrations. We're asked to find the rate equation and also the value and units of K, which is a rate constant. So what do we do in this situation? Well, first, we need to determine the orders of all of the substances before we do anything else. The way we do that is we maintain one of the concentrations the same. And in this case, as you can see, there are two 0.1 moles per dm cubed for substance B. So therefore, we choose to keep substance B the same while we find the order for A. As you can see, the concentration for B stays the same. So we only care about the concentration and for A and the rate. As you can see here, the concentration for A increases by a factor of 4. The rate also increases by a factor of 4. And we write the rate in terms of increase of substance A. So in this case, it's increased by a factor of 4 to the power of 1. And that power will tell us the order of substance A. In this case, it is 1. Now, we will do the same thing for B. As you can see here, we have a little problem because there are no constant concentrations for A. So what do? We need to cancel out the effects of A on the rate before we work on B. We already know that the order for A is 1. So in this case, A increases by a factor of 2. Therefore, the rate will also increase by a factor of 2 because of the increase of A. So we cancel that out. Therefore, we're only left with an increase of 2, as 4 divided by 2 is equal to 2. Now we look at the concentration for B. B's concentration increased by a factor of 2. And the rate after the cancellation, which we just calculated, is also equal to 2. And 2 is equal to 2 to the power of 1. And that power will tell us the order of B, which is 1. So now we have the rate equation in the form of R is equal to K times concentration of A to the power of 1 times concentration of B to the power of 1. Now we will find the value of K through substitution. In this case, we'll choose the first row. R in this case is equal to 5, is equal to K times the concentration of A to the power of 1, which is 0.1 to the power of 1, times the concentration of B to the power of 1, which is also 0.1 times the power of 1. Put that in the calculator. 5 divided by 0.1 times 0.1. K will be 500. We're also asked to find the units of K. And we do that through indices division. As we know, the units for rate is moles per dm cubed per second. And the units for concentration is moles per dm cubed. Therefore, we substitute everything in. We know that K is equal to the rate divided by the concentration of A to the power of 1 divided by the concentration of B to the power of 1. So therefore, moles per dm cubed per second divided by moles per dm cubed times moles per dm cubed. And you will end up with moles to negative 1 times dm cubed per second. And remember, the units of K should always have per second in it. Thank you so much for watching. Subscribe and join Dover Affinity to make a difference in your learning. Join us at Wednesday break at room 3S7.